together with Boris Hessing and Gerard Michiolik. And if you want to see details of what I talked about last time, with all the references and so on, and what I'm going to talk about today, you can have a look at it. Okay. So let me start with again with this picture that I had last time. Principal bundle picture. So we take some compact smooth manifold M. We look at the diffeomorphism of M. We illustrate this. It has a group structure, identity, and then we take the subset of volume-preserving diffeomorphisms. So we fix the volume form on M, and then we look at the subgroup of volume-preserving diffeos, called the volume form mu, so this is diff mu. And then I look at the quotient case, so diff over diff mu. Then the result, going back to Moser and then Hamilton as well, showing that in fact this is a principal bundle. The quotient you can identify with probabilities, smooth probability densities. It's a reference one mu. And then when you when you do this quotient, you can take the quotient either from the left or from the right. Okay? Then I'm going to talk about both those settings and discuss so here is the underlying, if you like, manifold setting or group setting. Now I want to attach Riemannian structures to this principal bundle. And then from that, you will get various equations and various metrics and so on. And then there will be the connection to the Fisher-Rao metric and information geometry. But before I do that, I want to talk about the connection to another field, another big field of mathematics, which is optimal transport. This is work going back at least to Brenier, with this idea of using L2 optimal transport for problems and relate that to fluid dynamics. And then Felix Otto, who was more explicit about the connection to Riemannian geometry and worked with this. Okay, so let's start now. Let's take let's take the action from the right. Okay, so we take the action of diff mu on diff from the right. Okay, that will be our quotient. So if we take any other point here, so that will be a diffeomorphism. It's associated with some coset fiber of the principal bundle, and that coset of eta is going to be then so it's from the right, so I take eta and then I compose it with this view. This will be in this set, and it's always a bit confusing because the eta is on the left here, so this is called the left coset. Okay? Later on, we will talk about the right cosets, and then it's the other way. And if you do it like this, then the mapping, the projection here will be just the push forward of the reference volume form of eta. Okay, so Now I want to give a Riemannian structure to this whole thing. And I do it in the following way. So I define some Riemannian tensor on this group of diffeomorphisms. Last time I did that as well. And then I showed you that if the Riemannian metric that you define is right invariant, meaning it's determined from just one inner product at the algebra, at the identity component of the group, identity points of the group, then you get the right invariant metric, and that gives rise to a set of PDEs called the Euler-Arnold equation. And I gave you one example, I think the Hunter-Saxton. I worked that out. So now we're going to do something similar, but one thing to realize that we want to give a metric here that descends to something down here. So what does that mean? It means the metric needs to be invariant under the action of this subgroup. Because this action is now from the right, it means that any right invariant metric will descend. But being right invariant is stronger than what I actually need. It's enough if I'm right invariant only with respect to this subgroup. Now I'm going to write down a metric that comes from physics, corresponding essentially to just taking the kinetic energy. If you fill your manifold with particles, and each of the particles have same mass, and then they move around, and then you sum up all the kinetic energy. Essentially, that's how you interpret. That's why this metric is important. Natural one from the point of view of physics, of particles moving on the manifold M. And it's the following, sometimes called a non-invariant L2 metric. Non-fully invariant. It will have invariance properties. And it's given like this. So I take two tangent vectors, u and v, to the space of diffeomorphism sitting above some point E. Okay. And then now actually I require my manifold M to be Riemannian. Use a Riemannian structure here. So I assume now that there's a Riemannian structure. Let's denote this Riemannian structure by T. Okay, so this is not a group element now. That's actually. And then I just take this one at phi of x, base point phi of x. It's a finite dimensional metric tensor, and I evaluate the corresponding thing here. Phi of x, and I integrate with respect to mu. This will be my metric. And if you think about this metric here, and you want to understand what are the geodesic equations, never mind invariance properties for now, just think about what are the geodesic equations for this metric. And notice that the only way that this depends on phi here is via the base point here, point-wise base here. There's no derivatives on u and v or on this. It's completely kind of local. It's completely pointwise, I mean. Okay? So therefore, if you just take this, you write down the Euler-Lagrange equations for this, what happens is that the equations that you get somehow is going to be equations for these maps, phi of x, right? And it's going to be a second order equation. And once you think about it, you see that what you're going to get is just the pointwise flow on your manifold. It means you get the map that takes some point x, and then takes a corresponding u of x, sitting above there, and just integrates along the finite dimensional geodesics to get to some point phi of x. You have another point, y, you have another initial vector, u of y, and this will map then to phi of y. So, yes, that's what we want here. So we have a Riemannian structure, so this would be the sorry, I didn't say. Let's call it mu. Okay, so that's just something about this geodesic equation. In particular, in the simplest case, when the underlying manifold is flat, then the geodesic equation is just going to be phi double dots, two time derivatives equal to 0. Very simple. Okay, but now let's talk about geometry again, and think about invariance properties. And one thing we can do is, okay, so we have now expressed this metric in terms of tangent vectors above this point here, but since we're on the Lie group, we can kind of take these tangent vectors and translate them back to the identity to get vector fields. Okay? So we can write this metric the following way. So we write it in terms of the corresponding vector field, so that would be lowercase u composed with v, and lowercase v composed with v at the point v, okay? And then we just plug in what this is. We use a change of variables on the entire domain. And what we get is the integral over now g applied to little u, little v, but then you get a push forward, because you have to apply the inverse to get rid of here, so you get the push forward here on mu. So that would be the formula for the metric expressed in terms of these generating vector fields for the tangent vectors. And this formula is useful because it shows us the invariance properties. Namely, if you take any diffeomorphism, compose it from the right, and you don't take any diffeomorphism. You take a volume-preserving diffeomorphism, compose from the right here. Then you can again use this change of variables, and the right composition here is going to do nothing if it's volume-preserving. So this is in fact equal to u of eta, so eta is now some volume-preserving diffeomorphism, v eta at the point phi eta, if eta is in a group of volume-preserving diffeomorphisms. So that's nice because it means that this structure descends to the cosets. So in fact, this metric is going to descend. Some metric down here on the space of probabilities, and see how much detail we give. We can do one thing. Here is the projection. Okay, it's just acting by push forward. So I can work out what its derivative is, and then I can work out what the kernel of the derivative is, and that will kind of give me the vertical directions. Once I have the vertical directions, I can work out the horizontal directions, because I now have a metric structure. Once I get the horizontal directions, I can work out what the metric is going to be, because I know by construction now this is going to be a Riemannian submersion if it is. So that's how this goes. So let's work out what the derivative is of this map. I take the projection, apply it to some diffeomorphism, and then evaluate it at some tangent vector, which I write as V composition phi, where V is a vector field. And then, if this, I can think of this as d dt of some variation of V in the direction V, this, this would be something like I to mu of this thing. Then now it's, calculus Lie derivatives to see that in fact this is minus Lie derivative V applied to mu. That's nice. What does that mean? Yes, yes. I identify tangent vectors with just equivalence classes of curves, and then that's how I get. Okay. So why is this interesting? Because now we can look at the kernel, as I said, of this thing, and you can already see it from the formula. Because what is the kernel of this mapping for the various v's? So which v's give us 0 here? Well, exactly the ones that are divergence-free, but now with respect to this volume form here, push-forward volume form. It means that the kernel at the point phi, okay, which is, by definition, this is the vertical distribution associated with this principal bundle. So let's call this V at C, okay? And this would then be equal to, what is it equal to? Well, V, it's a tangent vector, right? So it's generated by V, but at phi, okay? And then it has to be divergence-free with respect to this push-forward. If I call this element here rho, equivalent statement is to say that div, with respect to the standard volume form, mu of rho v should be 0. Okay, so that's nice, and now we know kind of these directions, vertical directions, in terms of the generators on the algebra. You kind of see, you see the non-fully right invariance coming out here, because somehow this here actually depends on the base point. But it only depends on it via this rho. Okay, so what I want to do next is I want to take the orthogonal complement to this part, to this distribution, and that will be my horizontal directions. So now I want to compute kind of these directions. That will be the horizontal distribution at this point. Okay, so let's then try to figure out what this would be. So let's see. Where is the inner product? Here is the formula. Here is the form I want to use. Okay. I now know the condition for one of the vectors. So let's write this as a condition. I have my my v, which I assume now that it fulfills this condition. I want to find the orthogonal complement with respect to it. So then, what is the condition on w for this thing to be 0 forward mu. Here, what does this mean? Well, this is just, I'm using again the so this should be 0. And you see that this is almost a Helmholtz decomposition, but a little bit shifted. In fact, this modification of the metric is exactly the modification you need in order for the horizontal thing to stay constant. So in fact, I claim here, and it's easy to check in one direction and you have a little bit of work to do it in the other direction, but I claim here that W has to have the form. In order for this to be 0, W has to be a gradient. So the kernel of this complement of the kernel is given by exactly by the gradient vector field. This would be grad f, or let's say some smooth. Okay, so that's nice. Now we have actually these directions. They're just the gradient vector fields. And we also know I computed the derivative, right? It was this one. So if I now take just a gradient vector field and plug it in to this formula for the derivative of the projection, that should give me the tangent vectors. So that means if I take d of pi applied to grad f, pi at phi, grad f I, this should be equal to a div, so minus Lie derivative, grad f let's call this again rho, and then I get the formula minus div of rho grad f. Okay? So this is my equation that takes me from a tangent vector down here, this point. Here's my rho. So I want to get from a tangent vector in the horizontal distribution down to a tangent vector here. Now I know, because I know what the metric is up here, I know that if I have a tangent vector corresponding to this f here, according to this equation, then I know what the metric is. Okay, so in the end, the metric that this descends to is going to be, let's call the tangent vectors alpha and beta. So alpha and beta are now tangent vectors in the manifold of probability densities above rho. And then I just use the formula for the metric. So this is going to give me integral over m of d grad f. Let's say grad f is the one corresponding to alpha, and then maybe grad g is not good now, h beta. And this should be integrated with respect to rho. Okay. I just write rho. And then the connection between this f and alpha is exactly by this formula. So I know that alpha is equal to minus div rho grad f, and beta is equal to minus div rho grad h. So this will be the metric downstairs. And what do you, to actually compute it, just look at it, what do you have to do? Well, you have to take your alpha and your beta, and then you have to solve for this solve this equation for f and for h, and then take the gradient and plug it into here. If you count derivatives, what is the Sobolev order of this metric? Negative, right? Sobolev h minus 1. This is an h minus 1 metric. And this is what we expect, because it was L2 upstairs, and we're taking derivatives to go down. This is metric is Wasserstein Otto metric. And why is it called like that? Maybe I should say about that. Well, because if you look at this structure here, this vibration structure, and you think about what horizontal means, and then you think about geodesics for these kind of Riemannian submersions, then there is a kind of thing that if you want the shortest geodesic between two fibers, it has to be a horizontal geodesic. Okay? And if you think about this in terms of a map, you know, that takes you from here to there, and you formulate it as a kind of transport problem, you see that exactly what happens when you solve this geodesic equation between the fibers is that you're solving the L2 optimal transport problem. Okay? So this is a Riemannian metric for which the corresponding Riemannian distance is the L2 Wasserstein distance. That's very nice. It gives a kind of Riemannian interpretation of L2 optimal transport. That was the first part. So this is the connection to optimal transport. And let me also say that kind of the connection to the standard Euler equations is what you get when you take the same metric and you just restrict it to this subgroup of volume-preserving diffeomorphisms. And then, of course, it's fully right invariant. It's restricting to the group where it is invariant. So one way to think about optimal transport is that it's kind of the orthogonal to incompressible hydrodynamics. Okay. Motion in optimal the optimal transport maps are moving orthogonal to hydrodynamic, to incompressible hydrodynamics. So let me now continue with the same picture, but for the pullback projection instead of the push forward. See where that can lead us.
Like the fiber space, you have a L2 metric. On the red space, you have H minus 1. And it is actually H minus 1 dot, which is, you don't really have one. Okay, like H.
H minus 1 dot is something else. That will come up. Well, H minus 1 dot, H1 dot is coming up soon. Okay. That's a different story. So let's draw the same picture again. If mu and vibration like before, except now I'm taking the projection, the quotient from the other direction. So now I'm taking the quotient from the left. Means I have right cosets. The projection pi of eta is given by pullback of the reference volume. It still works, still gives me an identification with probability space. It's still a principal bundle in the infinite dimensional Frechet category of things. But now, kind of these fibers, these cosets, are described by right cosets, which means I apply the subgroup from the left. If M composed with eta. So before I said, if you construct a right invariant metric, any right invariant metric will automatically descend with respect to any subgroup, in particular with respect to the diff mu one. And in fact, here I used that extra room to construct a metric, or it turned out that this natural metric has exactly the properties to descend with respect to this. But now the situation is different. I still want to work with right invariant metrics. Those are the ones we have in fluids. I don't want now to kind of tell you exactly the same story, but just from a left invariant point of view. That wouldn't give us anything, essentially. Just apply the inverse of the diffeo and you map from one to the other. I still want to work with right invariant metrics on diff amp. Okay? But you see, now being right invariant doesn't help you to descend. Okay? So you need something extra. So if you find, so the question is here, is there a right invariant Riemannian metric that stands? That's the question. It's not obvious. And if there is such a metric, it means it needs to have, in addition to these right invariant properties, it needs to have some sort of left invariance. In finite dimensional groups, you can construct a compact group, use the killing form to construct such a bi-invariant metric, and then motions from both directions. But now we're in infinite dimensions, and it's not so clear if there exists such a metric. And it turns out there is, and there are such metrics. And those are the ones I want to discuss. And in fact, I'm going to make life a bit easy, because I don't want to construct a full metric. I'm going to give you a degenerate metric upstairs. And remember last time when I talked about the Hunter-Saxton equation, I also didn't give you a full metric. It had a kernel, the metric. The situation will be similar here. Let me just say that there are ways to extend it to a full metric, but I'm not going to talk about that today. I'll just take the simplest setting of the degenerate settings. So here is the one that I propose. You take, again, two tangent vectors, V and W, of some point phi, like before, okay? And then I write this in terms of, again, I can write this, of course, in terms of the generators. So I write this in terms of little v composed with phi, and then W composed with Right? I want to say what this is. And I'm just going to give you a formula here. I fix some volume form, mu, still, and then I take the divergence of V with respect to that volume form. scalar, so I just multiply that with divergence of W, and I integrate with respect to mu. The divergence is also with respect to mu. So clearly, this has a big kernel. Well, in one dimension, it's not so big, as we saw last time. Constants. But even in 2 dimensions, it's kind of much bigger. But never mind that for now. Let's just try to think about what, essentially the same things we did before. Try to figure out if this matches. So the first thing I want to do is so now we have the projection I of phi is given now by pullback. So we want to compute derivative. We do it the same way, d dt. Now we have instead pullback. Then what happens, there's no minus sign, and the diffeo comes on the outside, so it's going to be this Lie derivative v. So again, this is good because it gives me the kernel here, right? I just read off, okay, if whenever my vector field is divergence-free with respect to mu now, a fixed mu point, right? Then this is going to be in the kernel. Now I know what the horizontal directions, and they're slightly different from before, because now it just depends on this fixed mu. So, yeah, let me actually take this formula here and write it. I'm writing things in terms of Lie derivatives. We write it slightly different. This is the divergence with respect to mu. So I can write this as what? 1/4. The 1/4. Okay, I will explain. But I write this as Lie derivative v on mu divided by mu, then Lie derivative w on mu divided by mu, integrated with respect to mu. These are 2 functions. You will see later why I do this, because essentially this will be my tangent vector downstairs. This will be my rho dot. And it looks a little bit like this thing here, right? But not quite, because I have this action. But that's fine, because I can kind of apply that to the entire thing. Okay, so this is the same as 1/4, and then using a change of variables by this diffeo, I can apply this to the thing here. W mu. Okay, so everything here is natural. I can apply the action of this on each individual thing here, and I get something which is exactly this: 1 for v and 1 for v and 1 for w. Okay, I call that alpha and beta, just like before. The formula I get is 1/4 integral m alpha divided by, not by mu, but by the pullback of mu, which is exactly the base point where I'm sitting. That's the rho. Okay, that's rho, and then beta divided by rho integrated with respect to rho. Anyone recognize this formula? Yes. Yeah, so I just make a change of variables in the integral exactly by the phi. So this is This is a volume form, right? So I apply that to this. And then I use that everything here is natural, so I can apply it on each individual thing. And that gives me this formula here. This is just calculus of fullbacks. So this is Fisher-Rao. Amazing, okay? And this metric is invariant under the action of the diffeos. Why is it invariant under the action of the diffeos? Because I started with the right invariant metric up here. So by definition, I didn't exhaust the right invariance to make it descend. Instead, I used some left invariant properties to make it descend. So the right invariance is still there. So I can still act on the cosets from the right. And that's going to be invariant. So in fact, by construction, this is right invariant. I don't even have to check it. It's easy to see also by checking. And so this is what Alice talked about. So I will not show you much about, maybe I should say something about that. So if you take the square root map from the space of densities to some part of the L2 sphere, then you see that what happens with this is that it becomes just the standard L2 metric restricted to the sphere. We know what the geodesics are on the sphere, so in fact we have explicit geodesics. And that's what Alice was talking about. And well, I can tell you, maybe I have some time, I can tell you some story about this. Some of you know that we had for a long time, since I think 2012 or something like that, we had these Math in the X meetings, which is kind of meeting about shape analysis. And the first one was in New Zealand. The second one was in Austria, here. And on the way there, we were driving there. Martins Breveris, some of you know him. We were discussing this Fisher-Rao. There was a kind of interesting thing. And I think someone mentioned, like, oh yeah, but you know, Fisher-Rao is unique. And he said, why? Why is it unique? And I think, yeah, but you know, it's the old result of Chenkov and so on. Yeah, but that's in finite dimensions. How do you know it's unique in infinite? And then that became a problem that Peter and Martin then solved. Yeah, that was an intriguing, nice story to see how this. It turns out that it is actually up to scaling. This is the unique metric on the space of probability densities that is invariant under the group of. And the one fourth here, I should just say something about that. That's just, I think, to get the standard L2 metric when you take the square root. So, yeah. I mean, sometimes I look at this, I draw this picture. I don't know how many times I've been drawing this picture. It feels like I've been stuck with this picture since that year, 2012. Always the same picture over and over and over again. But it is kind of very nice. It's very rich. There's a lot of geometry. Okay, let me say the final thing. So now I want to connect back a bit to what I talked about last time, namely the Euler-Arnold equations. You can take this metric that I wrote here, and never mind this principal bundle, just think of it as some sort of degenerate metric, right invariant metric, and you can write down the Euler-Arnold equations. So if we do that, you remember you have to compute this add transpose and so on. And once you do that, you have to take the derivative of the. Once you have that, then you essentially have the equations in motion. If you do that, write down the Euler-Arnold equation for for this metric here, which by the way is often called H1 dot. So H1 because it's obviously an Sobolev H1 type metric, and dot I guess because it has this singularity or kernel, so it's not really a metric. The Euler-Arnold equation for H1 dot, not going to do it in detail, let me just write it. It's going to be, one way of writing it is like this. Grad div, not div grad, grad div of the vector field, u, with a time derivative on it, ut, plus div of u times grad div u plus gradient of u paired via the metric with grad div 0. This is the Euler-Arnold equation. And if you take dimension of m to be 1, you compute this, you see what you get. You get utxx plus 2 uxx plus uxx equals 0. This is the Hunter-Saxton equation. So that is the connection between the Hunter-Saxton equation, which was developed in physics as a kind of equation for describing the vector fields, if I understand. And here is now this, via geometry, you get this beautiful connection to Fisher-Rao. And then it was Jonathan Lenels who first made this connection. And he was, I guess, he was studying this equation and trying to understand it in terms of integrability and in terms of this Euler-Arnold structure. And then he was probably somehow trying to compute curvature, or maybe he was just realized this some other way. He realized, oh, with this square root map, I can simplify this a lot. And he came up with this result that the Hunter-Saxton equation describes some geometry, and the curvature of this geometry is positive and constant via this mapping. And then that was generalized a few years later to this equation and to this description by Jonathan Lenels, Boris Hessin, Steve Preston, and Gerard Michiolet. Okay, I think that's all I had. Thank you very much for this mini course.